Okay. What we also have here is that we have a map that is invertible. Okay. This isoparametric map is invertible. Okay, and the reasons for it being invertible, if you really care about it, is because we have a or just a different way to state it is that it's a one-to-one and onto map. Okay, therefore it's invertible. Okay, because it's invertible, what this means is that c comma x is just 1 over x comma c. Okay, first of all, it means that c comma x exists and that it can be written as just 1 over x comma c. This statement will become a little more meaningful and significant when we go to multiple dimensions. Okay, we'll have to have actual tensor maps, and those will have to be properly invertible and all that. All of that will be assured too. Okay, but let's just lay the groundwork for that discussion when we get to it. Okay, so why do I care about c comma x? Because now what this lets us do is to go back and write comma x as sum over a n a comma c comma x d a e and comma x sum over a n a comma c comma x c a e, right? It lets us say that this is just 2 over h e. Okay? All right. As the very last thing to do in this segment, I want to just begin assembling some of these integrals that we need to worry about. Okay? So, consider the integral, or consider the following integrals, okay, which come from our finite dimensional weak form. First, consider this one, integral over omega e wh comma x sigma h a dx. Okay, putting everything together, we have this as being written as integral over omega e wh comma x. Now I'm going to invoke our constitutive equation, okay, and I'm actually going to move the area into this and write it as okay. See what I've done? E times u h comma x is sigma h from our constitutive relation. Okay, and this I'm now going to write by bringing in our expressions on just the line above for UH comma x and WH comma x. Okay, I'm first going to write WH comma x. It is sum over A. I won't write the limits on A because it gets just too clunky. Okay, we know now from having looked at it over the past couple of segments that A runs over the limits 1 to number of nodes in the element, which in the simplest of cases is 2. Okay, so I have that. I just won't write the lower and upper limits. Okay, I'll just say that's a sum over A. Okay, n A comma c times 2 over HE C A E. I'm going to put parentheses here. I have E A, okay, open parentheses, and here I have another sum, but I need to be careful here and use a different index for the sum, so I will use the index B and not the index A. Okay, the sum over B, NB, comma C, 2 over HE D B E, close parentheses, and observe that I shouldn't forget the fact that I have a dx here. Okay? In writing this first set of parentheses is my representation for WH comma X. The second set of parentheses give me UH comma X. All right? And then I have the other integral, which is actually a somewhat simpler one, integral over omega E, WHF function of X, which could be written as, which can be parameterized by C, A, dx. This is somewhat simpler to write. It is just integral over omega E, summation over A, and I will stop writing the limits on those sums. NA, no derivatives here. Okay, NA C A E. I put parentheses on it. F, perhaps a function of X through C. A dx. Okay, this is what we have, right? As a very last thing, let me just do one more thing here. Observe that essentially everything that in these last integrals is parameterized in terms of C. Right, the NAs are parameterized in terms of C, and we can also compute their derivatives, right? They turn out to be constants, we know, but we can compute their derivatives, can view everything as being parameterized by C. Except that we have this as the as a length element, right? Well, but then we can use the chain rule there, right? So we're going to write that as dx dxc, dxc, right? And obviously the same there. Okay, but after all, what is dx dxc? On the previous slide, and actually we have it in some form up here too, right? We see here that we saw c comma x is 1 over x comma c. Right, and here we have what c comma x is, right? So what we see is we've already figured out that dx dxc is he over 2. Okay, the same thing there. Okay, what that will let us do is to rewrite these integrals as integrals over the bi-unit domain omega c. Right? As a very last step that we are going to take in this segment, I'm going to write that. Okay? What this lets us do then is write integral over omega e wh comma x e a UH comma x, and I'm writing this already in the form that we will, where we've implemented our constitutive relation. Okay, this is, now we can write this as an integral over omega c. We have sum over a, na, comma c, 2 over he, c a e, close those parentheses, ea, open another set of parentheses, this is a sum over b, n, b, comma c, 2 over he, d, a, e. Now we have dc dx, but that we know is he over 2 dc. Okay? And of course, what we are going to do when we come back is to observe that these two cancel out. And likewise, we have integral over omega e wh f a dx can also be written now as an integral over the bi-unit domain of sum over a, na, c a e, f, which we may eventually want to write as a function of c, a. Now we have dx there, but we are going to write that as dx dx, which we know again is he over 2 dx. Okay, that's what we have for the main integrals that go into our finite dimensional weak form. So this is a good place to end the segment. When we come back, we will focus upon evaluating these two integrals.